Hi, and welcome back to another episode of Amiga game programming series. Last time we created level background using tiles technique in ProMotion NG, then exported it for format suitable for using in our code. We also had to tweak IFF image in Deluxe Paint to reduce colors back to 16, which will become very important in this episode. And today we're back coding. We will set up copper list and start rendering tiles we created last time. Towards the end of episode 2, we were left refactoring the code. But during fiddling with copper, I realized the code needs even more structure. But I don't want to bother you showing the process, so I did it off screen and will just quickly go through results. Overall, I'm quite satisfied with what I came up to. The code is even more structured now and, more importantly, establishes stronger conventions. Opposite to hard rules imposed by programming language, compiler, and hardware, conventions are a mixture of good practices from programming community and experience of oneself. By following similar approach throughout a program, it makes code easier to understand when switching context. After many years of programming in higher level languages, I can easily establish different patterns there. But I don't have nearly as much experience with assembly, so it took me a while to start recognizing patterns here too. As you can see, application code is simpler and divided into smaller subroutines now. Another thing of notice is all subroutines use kind of reverse domain naming scheme. First word of the name indicates the system subroutine belongs to. Assembly language program is basically just a list of instructions. It lacks sophistication of namespaces, classes, and similar constructs of higher level languages. Using this naming scheme will help in adding some of the structure. Okay, this brings us back to copper. This file includes copper list itself, as well as couple routines for managing it. One thing I didn't discuss so far, but you may have noticed, I am quite generous with commenting the code. I find assembly programs less readable in general. Even though one part of the code may look very similar to another, they may do totally different thing. I'm also not regularly programming it, so I want my future self to understand what exactly particular part of code does, what registers it changes, and what values they hold on, and so on. This would also be a good point to start discussion on copper lists. As mentioned in past episodes, copper is general-purpose coprocessor in one of Amiga custom chips. It can control almost entire graphics system on Amiga. It expects program to pass in the pointer to a list of instructions which it then executes independently of CPU, thus freeing it to execute program logic. The whole list of instructions is executed as video beam travels down the screen. Copper only understands 3 instructions: wait, move, and skip. This may seem limiting, but you can do a lot with them. Wait instruction waits for specific screen position. It is usually followed by one or more move instructions which actually change special purpose registers. Skip is not used that often. It takes specific screen position as argument and then skips next instruction in list if video beam has already reached given position. Each instruction is formed with 2 words. First line is a move instruction that sets special purpose register for color 0 to black. Color 0 is used for background. As this is the first copper command in the list, it is executed at the top of the screen. As consequence, whole background will be rendered black unless we change the color along the way. In second line we have a wait instruction. It waits line hex 96 or 150 decimal, which is around middle of the screen. This may come as surprise given our vertical resolution is 256. There are actually 312 possible vertical positions in PAL, or 262 for NTSC. That's because computer monitor is partially covered behind housing. This also means the top of the screen as we see it doesn't start with line 0, but rather around line 28. After waiting for line 150, we change color to yellow, wait 2 more lines, and change back to black. This will result in yellow line 2 pixels tall in the middle of the screen. We must always end copper lists with wait instruction where first word is hex FFFF and second hex FFFE. This describes position that will never be reached, and thus instructs copper to stop processing until next vertical blanking interval. At that time, it will repeat the whole list and do that again and again, 50 times per second for PAL or 60 for NTSC models. Alright, this was quick and dirty copper list introduction. I also mentioned vertical blanking and video beam couple times already. If these terms are new to you, or you're simply interested, feel free to check the video on how TV works. Find the link in the description below. I also included a link to Sprite Tricks website. It describes tricks programmers use for achieving various effects in Amiga games. Interesting and informative read for getting an idea of what Amiga is capable of. We'll use copper for adding various effects of our own later on too. But for now, let's see what this copper list produces. And there you go, 2 pixels tall yellow line on otherwise black background. Remember my promise of degraying the screen from episode 2? Well, here it is. Always keeping my word. Before setting up any drawing, let's define constants for our window. I try to avoid hard coding values as much as possible. This way, impact of change is kept to as minimal as possible. In here, we define our window size, number of bitplanes, and couple dependent values to simplify calculations later on. But what exactly are bitplanes? Amiga screen display consists of 2 basic parts, Playfields and Sprites. We'll talk about Sprites in later episodes. But let's discuss Playfields before diving into level background rendering code. Playfield is where we draw game background. We form it from 1 or more bitplanes. Each bitplane is composed of series of bits, 1 for each pixel. And when system combines all bitplanes for display, the combination of these bits form the index of the color register for that particular position. There are 32 color registers available. So we choose number of bitplanes based on desired number of colors we need. Single bitplane yields 2 colors, background and foreground. 2 bitplanes allow up to 4 colors, 3 bitplanes up to 8 colors, 4 bitplanes up to 16, and 5 bitplanes all 32 colors. Keep in mind though that of 32 available color registers, top 16 are always used for sprites. So, if we want to use all 32 colors for bitplanes, we will share top 16 with sprites. This can easily be handled with careful planning of our palette, but if you have to rely on pre-rendered background tiles, as I do, it can become more complicated. That's why I opted to only use 16 colors for background. Typically, bitplanes are interleaved in memory as shown on this graph. Each screen line is represented by all bitplanes in successive order, then followed by next screen line data, and so on. This means bits defining each color are not stored together, which can make it quite confusing. But it conserves memory as we only need to allocate it for as many bitplanes we'll use. Luckily, Amiga hardware comes prepared for dealing with this kind of setup. Amiga hardware manual describes Playfields really well, warmly recommended. You can find the link to online version in the description below. Now we are equipped with knowledge to discuss those constants. We want to use 16 colors for Playfield, therefore we need 4 bitplanes. We need to know the size of each bitplane line in bytes, so that we can calculate offsets for next lines. Our bitplanes will match window size exactly. Given each pixel is represented by single bit in the bitplane, this means we can simply calculate byte size by dividing width by 8. In addition to line size, we also need to know the size of the whole bitplane in bytes. Now that we have the size of individual line, we can multiply it by 8. One neat feature of Amiga Assembly plugin is display of values. Just hover the mouse over any variable or constant, and it will show the value. It will even calculate the result based on the equation. Additionally, you can enter your own equations on the fly using command palette. Press Ctrl Shift and P and type calculator. Then type in your equation. You can enter values in decimal, hexadecimal, or binary. We have all prerequisites in place to implement window initialization and cleanup. More specifically, we need to write subroutines for allocating and freeing memory for all bitplanes. To allocate memory, we use appropriately named allocmem function. Allocmem requires two parameters. D0 holds the size of memory to be allocated in bytes. For this case, that's the size of single bitplane multiplied by number of bitplanes. We also need to specify the type of memory in D1. Amiga has chip and fast memory. The difference between them is that chip memory is shared between CPU and custom chips, while fast is only accessible to CPU. We need to have bitplanes memory accessible to custom chips for rendering, therefore we must allocate it in chip RAM. Allocmem is exec base function, so we need to call it relatively on exec base address. We copy base address to A6 register and call the function. Result of function is pointer to allocated memory in register D0. We need to remember it as we'll use it throughout the application, so we copy it to a variable. Allocation may also fail. In this case, we would have to show an error and exit. But for simplicity, this code assumes allocation will always succeed. To clean up, we need to free allocated memory. For that, we use freemem function. It requires memory size in D0 register and pointer to allocated memory in A1. And of course, we need to call these two subroutines from application setup and cleanup. Allocating memory for bitplanes is just the first step. We still need to configure the system to use this memory for drawing, as well as cover other parameters. We use special purpose registers for this. We'll set the values in copper list, though we could just as well do it by directly assigning registers elsewhere. The advantage of using copper is that we can dynamically change these values for achieving various effects. Bits 14 to 12 of BPL cont 0 register are used to specify the number of bitplanes. Using hex values makes calculation quite simple. Number of bitplanes is multiplied by hex 1000. The only other bit we set is 9. It is used to enable color on composite display signal on Amiga 1000. It doesn't affect RGB signal that's used for connecting to monitor. Next two lines define size of display window. DIW CTRT contains start position. It's restricted vertically to top 2/3 and horizontally to left 3/4 of display. DIW stop specifies end position. It's restricted vertically to lower half and horizontally to right quarter of display. They both use the same bit representation. Next, we have to tell the system on-screen location for data fetched from memory by describing horizontal position where each line starts and stops. I use standard values for low resolution mode. We also have to define modulo for bitplanes. Modulo is frequently used for various graphic-related functions. It's a number that is added to the address at the end of each line, so that the new address then points to start of next line. In our case, we need to skip 3 bitplane lines. BPL1 mod specifies modulo for odd, while BPL2 mod for even-numbered bitplanes. This allows setting up different modulos for dual playfield mode. But for single playfield, as we use, both numbers are usually the same. And last, we have to tell the system the address where data is stored in memory for each bitplane. As we're already used by now, each address is specified by high and low register. But there's one important difference with this set of registers. Their values are changed as data is read for display. Therefore, we must reset them to the beginning of bitplane data for every vertical blank. Now, we could do this by waiting beam to reach end of screen, as we did in game pause loop. But that would spend precious CPU cycles. That's where Copper comes to play. As mentioned earlier, it executes all instructions in the list for every vertical blank. So that's ideal. We just have to set values once, then Copper will take care of resetting them when needed. But there's slight issue. We don't know the address until we run the application and allocate memory. So we set all addresses to 0 and we'll update the values at runtime. Oh, another thing before we proceed. Note how we added Copper window Bitplanes label just before the first address instruction. It's not just a decoration, it serves real purpose as well. As we will have to change this data dynamically, we need to be able to find the exact location in memory. By using a label, we can always refer back to it, and it will always point to correct location, even if we add instructions above. Updating Copper list dynamically is common enough operation to warrant creating helpless subroutines for it. The first one is used to change a pair of instructions representing a write to a memory address, so that it points to any given address in chip memory. As all special purpose registers are 16-bit, we always have a pair when representing memory addresses. The subroutine accepts two parameters. A0 points to address we want to copy to Copper list, and A1 is a pointer to first word of double write instructions inside Copper list. We already have low word of the address in A0, so let's do a word move of it to an offset of 6 bytes after the address to which A1 points. Note, we again use register indirect with displacement mode, but this time with hard-coded offsets. I told you you'll see me using it all over the place. Then we swap both words of our source address in A0 and again use a word move, but this time to high position at offset 2. And that's all there is to it. It may have passed without realizing, but we actually created self-modifying program. So we need to be very careful what values we pass in for destination, as we can easily write into some area that will not have a very nice outcome, to say the least. Copying multiple addresses is quite similar operation, except that we increment source and destination pointers after each address. Caller needs to provide number of addresses to copy in D0 register, as well as source pointer offset to add after each copy to reach next address in D1. We'll use the value in D0 as indexer for loop. However, we need to subtract 1 in order for loop to work correctly. We'll see soon why that is needed. This part is identical to single address copy. First, we do a word move for low part of address, then swap words in source, and do another word move for high part of the address. After we copied source address to destination in Copper list, we have to set up pointers for next iteration. First line adds offset to source address. This is the argument we passed into subroutine via D1 register. We also need to update Copper list pointer for next pair of addresses. This is what happens in second line. We have to skip 2 Copper instructions. As each instruction is composed of an instruction word and data word, this means 8 bytes. The only thing remaining is to continue the loop or exit. That's what dbf instruction does. The mnemonic stands for decrement and branch if false, so we can test, decrement, and branch with single instruction. By the way, there are also other variants of this instruction. For example, dbt, decrement and branch if true, dbeq, decrement and branch if equal, and so on. Now that's where convenience of CISC versus RISC architecture really shines. You really can't feel it when programming in higher level languages. But let's get back to the code. As name implies, dbf decrements given data register, D0 in our case, and then tests if the value becomes negative. If not, it loops back to the label we provide as second parameter, .next in our case. If value does become negative, then it exits the loop by proceeding with following instruction. Note we use dot as next label prefix. This makes the label local, only visible within the scope of a subroutine. It's a convenient way of reusing the same label multiple times in the same codebase, as long as it's not in the same subroutine. Now that we have both helper subroutines implemented, let's use them to actually update our copper list with concrete pointers for bitplanes. We'll copy addresses for all 4 bitplanes, so we'll use second subroutine. As mentioned earlier, it expects 4 arguments. First, we need to tell it the number of addresses we'll pass. We do it via the 0 register. Then, we need to tell it how many bytes to skip to calculate address for subsequent bitplanes. We already calculated the size of each bitplane line, so we can simply use this value. So why do we need single bitplane width in bytes? Well, remember when we discussed window modulo earlier? This is similar to that, except that for modulo we had to reach next line of the same bitplane, while here we need to reach the next bit for the same screen line data from the following bitplane. Oof, mouthful, hope it makes sense. As said before, this can become really confusing really soon. We also have to provide source and destination addresses. Source is of course the memory we allocated for our bitplanes data, and destination is the address of the label we placed in our copper list earlier. I don't think I discussed this before, but in case you're wondering why you used #sign for some move instructions. #sign is a convention to tell assembler that we want to copy a value. Without hash, it means we're passing a pointer to address that holds the value. In later case, the actual value copied will first need to be read from the given address. But all that remains for us is to jump to our subroutine. We did quite a bit of coding. Let's see what it does. There's some garbage on screen partially covering background, but it's just black, even though we specified 4 bitplanes and thus 16 colors. Well, it all makes sense when you think about it. We just allocated memory, but didn't change any of it. And we also didn't set any colors, so they are all filled with 0, which is black. Let's do something about it. First thing first, let's add some pattern data to bitplanes so we can test. I won't explain this code, it's just temporary measure, but feel free to pause the video and inspect it if you wish. It doesn't look any different from before, which raises suspicions. But let's add some colors as well, perhaps it's just coincidence. We'll add colors to copper list as move instructions to corresponding special purpose registers. Yeah, we can see colors now, but data still looks random. Definitely not what we entered. And it also looks like there's single color only, as if only one of the bitplanes has data on it. I'll spare you with all the time I spent debugging this issue. I tried changing the pattern, colors, but with no significant change. I then changed to just clear bitplanes memory by filling it with zeros, and yet there was still garbage on screen. I also found it strange that sometimes emulator would remain stuck after pressing escape instead of closing, which ultimately got me thinking. This is clear indication I'm writing into some memory I shouldn't. And in this case, I'm clearly not writing into memory we allocated for bitplanes. I mean, it makes total sense. That's why garbage remains on screen despite all my efforts. The code writing to bitplanes memory seems okay, so the issue must lie somewhere else. This is definitely a case for close inspection with debugger. So let's add a breakpoint to our setup subroutine and run the app in debug mode. Oh, wait a second, this value looks strange. A1 register, which holds the address of bitplanes pointer, has a value of hex C00000. This seems way too high for chip memory. Let's check the value of the variable itself. And sure, it's hex 3DD0. Now it makes sense. I made mistake with move L instruction for setting up A1 register. I should have used hash in front of the variable. But let's use LEA here. It's basically the same, but it does emphasize the fact an address is being copied. Restarting and keeping all my fingers crossed. And would you have guessed it, it works! A1 has correct value now. Okay, also the final test, let the program run. And there you go, no more garbage on screen. That was expected as currently we just cleared the whole Bitplanes memory. I can't believe I literally spent almost an hour debugging this issue. But that's how programming sometimes works. You revolve around the problem in circles, coming back to the exact same place again and again. And then you just take some time off or look at the problem from another point of view and you suddenly realize the solution was in your face all this time, you just didn't see it. Let me quickly check again with some patterns to make sure all is indeed fine if we put some data to Bitplanes memory. Yes! Okay, let's also change colors to get some more variation. Ha! Now we're talking! Now we can prepare everything for rendering actual tiles. First thing first, we just need copper instructions for assigning colors. But we'll set this up after loading the tiles. And of course we also need to add labels so we can reference this exact area of the copper list, just as we did with Bitplane pointers above. Copper is now ready. Let's remove test code for filling Bitplanes with data. But let's leave the part that clears memory. Note that we use a trick for faster operation. Instead of clearing 1 byte at a time, we clear 4. This is fine because we use 4 Bitplanes, but will break if we change that in the future. This code also doesn't belong to copper setup. We should move it to window functions. But for now it will remain here. We'll very likely remove it shortly. With all these changes, I expect to see just black background with yellow stripe in the middle. No artifacts from Bitplanes. Let's run the app to verify. Cool, it works! Note that while the screen looks exactly like it did before we added Bitplanes, now it's actually displaying Bitplanes on top of background. Well, transparent Bitplanes, but still, we are controlling the display, and that's the most important. I was planning to start coding tiles in this episode, but it took me way too long just to set everything up. And I want to keep the videos reasonably short, so I'll wrap it up at this stage. On the upside, we have everything prepared for rendering, and that's what we will work on next time. As usual, you can find all mentioned links in the description below. Thanks for watching. Until next time, goodbye.